different? And then how can that exposure occur? So how does it change over use of a chemical? What happens across the life cycle? So again, medicine is a great example. Your doctor or your pharmacist will give you medicines to treat some hopefully very minor condition that you have, and then you take those medicines for a period of time. But then what happens to those medicines after you've taken, you become better? So if you have 10 pills left over, that's a chemical. For example, contaminate the water systems that were that are sustaining our drinking water, for example. What low impact design could deliver the same function? And so again, this is coming back to the top example. So what function is being delivered? And so we can think about, and this is where very creative scientists like you and crowd can think about new ways to deliver the same function with different molecules, right? So what you have to understand is what is the role of that molecule? What is it playing in this device, for example? And if you can understand what role it's playing, then you can maybe deliver that same function with a different chemical. And if you design in the green chemistry principles from the beginning, that design feature might make that process much more sustainable over a period of time, right? So this is design and function combined with each other. Okay, so what we're gonna go over is some different types of plant disasters. So these are commercial plants, most of them based in North America, but there's some, one example in China that I put in as well, and actually one in India. So again, not to point out the fact that these are bad companies or that they were irresponsible, but just sort of to use it as a highlight as to how we can use these examples to improve things going forward. And the important thing is then to consider also examples where the life cycle is hidden. And that's, for example, what I said before about the medicines, right? The medicines are a life cycle example where there's a hidden cost, whereas the plant disaster is a very visual cost that we can easily see to society. But there's a lot of life cycle consequences that are invisible, and that includes things like consumer products where BPA and endocrine disrupting chemicals can be part of those plastics that can be problematic. Industrial scale, so what we're talking about here is that the use of human resources, natural resources over the last 50 years has essentially exploded. So we are consuming much more. The population of the earth has exploded. Use of petroleum-based products has exploded. And so that industrial scale, the great acceleration of these resource consumption is greatly affecting our ability to think about green chemistry and to implement improvements. Well-intentioned fixes, and so this is another examples of unintended consequences. So biofuels, water treatment, photovoltaics, these are all exciting new directions for us to go to have a more sustainable chemical economy, but they come with unintended consequences, right? They're not perfect in and of themselves, and that's why there's new solutions that still needs to be considered, and we'll talk about a few of those. And then green chemistry, and so this is essentially where we'll start with the concepts of green chemistry and how they are applied, how we can apply them to understanding processes going forward. So there's a few examples of catastrophic plant disasters. So this is Bhopal in 1984 in India. And so essentially it's an isocyanate, methyl isocyanate. It had a large storage tanks of methyl isocyanate that was, there was a contamination with water that entered into those tanks, and causes an exothermic chain polymerization reaction. And that reaction led to essentially thousands of people dying immediately from that process. And there's even more that suffered, many more than that, that suffered long-term consequences. And so essentially what was the take-home message from this is that storing something so reactive in a site that was not using it on an ongoing basis is something which is inherently more dangerous than required. And then the process that was implemented afterwards was that we could just import the methylisocyanate more on an as-need basis, so you didn't have large storage tanks of those. So it takes more planning to do that because you can't just go to your vat of methylisocyanate out in the back. You have to actually have it delivered as you need it, but the safety of that increases exponentially because you don't have the possibilities for uncontrolled reactions. So this is the design lesson. So large inventories amplify consequences. So that's what we want to try to avoid. Highly reactive ingredients, and again, how do you know that it's a highly reactive intermediate? Well, it's your understanding of chemistry, molecules, and understanding how molecules behave. And so knowing that some molecules are more electrophilic or less electrophilic, more nucleophilic, less nucleophilic, that's a very chemical way of understanding things. Safety systems can fail, and so that's where having redundancies in your safeties systems, so you don't want to have a single safety system, you want to have multiple layers of safety so that you don't have to worry about a single failure causing larger problems. And then inherently safe design. And so again, this is thinking about designing safety from the beginning of the process as opposed to trying to back design after you have a process in place. So the back design costs a lot more in terms of resources and retrofitting than if you just design safety in from the beginning, even though there's a higher upfront costs. The Cuyahoga River, this was in Ohio in the United States. And essentially, this was along an industrial path. So these were all industrial buildings that fed into this river. And they were just essentially without any treatment, disposing of all of their waste products from their manufacturing process in the river, such that the river essentially was a thick soup of sludge, so very thick. It was completely unswimmable, and essentially it was all organic matter that was occupying, displacing the water, so much so that a fire lit the whole river on fire, and essentially became one of the early symbols in 1969 of industrial waste entering into our water streams, and the fact that we can't continue this way. And so essentially wastes are treated as an externality. In business language, an externality is something which society pays for, but the company doesn't pay for. So essentially the company is making profits from the chemicals that are being generated from their manufacturing plants, but the costs of those chemicals, the externalities, are being shared by society, and they're not being paid for specifically by the corporations. And so that's a market failure, they call that in economics, and it's a good example of how markets are not always the best solution to all of our problems. And then in Tianjin, in China, there was a container storage station which killed 173 people, and essentially it's very similar to the Bhopal accident where there was large inventories of ammonium nitrate that were cut on site, and that ammonium nitrate, sodium cyanide, calcium carbide, and other hazardous materials. And so there was a secondary explosion, and you can see from the that explosion essentially burned out all of these cars that are seen in the foreground. So again, having incompatible chemicals, so some of these chemicals are incompatible with one another on the same storage facility is something which is better to design in features to make sure that we're building a storage facility for this chemical, we're building another storage facility for another chemical. Are these two chemicals compatible with one another? Are they highly reactive with one another? Should we be doing this on the same site? Right? It's sometimes, and again, this is where chemistry becomes so important, right? Is that from an engineer's perspective, if they're building a storage facility and calcium carbide and sodium cyanide, to them, they both could be white powders, right? And that's the way they think about it, is that here's a white powder and there's another white powder. What's the difference between those two white powders? Just build a tank for this one and build a tank for that one. But we know as chemists that sodium cyanide white powder and calcium carbide white powder are very different, right? And that's where it's like being able to understand things at a molecular level is so fundamental to being able to make safe processes in the chemical industry. Okay, so so the recurring incidence of chemicals historically could have been seen as ordinary, and there's many injury-causing incidents that involve familiar high-volume chemicals. So, for example, carbon monoxide in homes, at least in North America, I'm not sure in Brazil, but that can be a big problem through the heating systems that we generate. And so they can create carbon monoxide, which is essentially an odorless gas that can kill because it displaces oxygen. Ammonia for agriculture and refrigeration, which I think can be a Brazilian issue. Chlorine, so for water treatment. So even though we think that we can just purify the water, but then we purify that water with chlorine a lot of times, and chlorine has its own issues. So that's again the cost-benefit analysis. Hydrochloric and sulfuric acids are used in manufacturing and processing and transport of a lot of chemicals. Again, they have unintended consequences. So essentially what we're asking is, can the same function be delivered with lower hazard, lower exposure, and lower inventory? So all of these things have to be taken into consideration. Not one of them is necessarily going to solve the issue, but there's going to be a lot of different industries will require different solutions. Okay, so the consumer products and such as BPA and endocrine disruptors. So this is sort of, you can see in a lot of different cases. So in canned foods, sports bottles, in the receipts that you get from grocery shopping, for example, children's toys, different types of polycarbonates. You have essentially the BPA, which is added as a plasticizer, so to make it a little bit flexible for these different toys. But the BPA is essentially associated with endocrine activity, so essentially can affect the endocrine system. And so this affects fish reproduction and has a lot of other negative consequences. So again, BPA is not a special chemical in and of itself. Right? So we know we can look up the structure of BPA, but BPA is being used for a specific function, right? So that's what chemists need to think about, is that what is bisphenol A used for, and can we design a different molecule that does the same thing, that has less unintended consequences, which is the endocrine disruptor that bisphenol A has. The flip side of this, and this is one of the things that's like challenging in a lot of areas of chemistry, is sometimes the new thing that we design, we don't learn of its unintended consequences immediately, because we can't test new materials for every possible negative outcome, right? So we can design a new material that behaves like bisphenol A functionally and is not an endocrine disruptor. So that takes care of two very important things that's problematic with, well, the positive thing with bisphenol A and the problematic thing about bisphenol A. But the problem is that when we design bisphenol X, let's call it, if we design bisphenol X, we know it's not an endocrine disruptor, but we don't know all of the. That's one of the issues with trying to design new and improved functioning materials. It's very hard to test for every single Good. Works. Okay. Maybe I'm going to leave this off. Everyone can hear me? I'll try to speak as loud as possible. In theory, it's a really great way to think about things, right? Is like the problem, solve the problem by creating a new material that doesn't have the same problem. But that doesn't mean that the new material can't have the same function and a new problem, right? And so that's a very important concept, is that it's overly simplistic to think we can design new functional materials that are completely free of all problems. The question becomes is that, are the problems of the new material significantly less than the problems of the current material? I think that's the better way that you need to look at when you're looking at it from a green chemistry perspective. So again, this is not meant to be that you look at every single one, but it's just to give you a bunch of examples of everyday chemical classes that have been identified as potentially problematic, from organotins. This is particularly applicable to the chemistry, the synthetic organic chemistry that we do in our lab, where we're trying to modify organotins so that we don't need to use them in palladium-mediated cross-coupling reactions. But there's also all of these other areas where synthetic chemists, not only synthetic chemists, but all chemists are needed to solve some of these problems. Some of these have been improved, created other problems that need solutions going forward, and but essentially things going in the right direction. Persistent chemicals. So this is a very important thing in terms of a good example is polyfluorinated hydrocarbons. So these are long chain organic carbons with a lot of fluorine atoms. So typically 10, 12, 16 fluorine atoms. And these are highly persistent chemicals. So they don't get decomposed by bacteria, viruses. They don't by any sort of natural processes. And because of that, they essentially just accumulate over time. And that becomes very problematic because then our Earth, which has a finite capacity to handle all of these chemicals, if it's just going linearly up and never coming down through any sort of decontamination process, it becomes very problematic. So that's where the design implications has to come into play. So can we design things that have the same positive properties as these polyfluorinated hydrocarbons, but don't have the negative consequences of the persistence environmentally? So again, I alluded to this before, and the data is a little bit out of date, but I can assure you that nothing has changed. So if you look at from 1950 to 2000, that's the population of the Earth versus the previous 200 years, right? So we were pretty flat for about 200 years. And then over the last 50 years, it's just been a straight up curve. The real GDP, so how much essentially the Earth is producing, this is an indirect measure of how much stuff that we produce also has gone straight up. Transportation, straight up. Fertilizer use, straight up, right? So this is something which we've never seen in the history of the Earth, and consequently, the things that are negatively impacting us environmentally, atmospheric CO2, nitrous oxide, the temperature on the Earth, average temperature of the Earth, particularly relevant to Brazil, tropical forest loss, has seen a huge increase over the last approximately 50 to 100 years, and it's continuing to go up. And all of this is, you know, we can philosophically argue about this, but unless we're going to start vaccinating people from having children, it's going to be hard for us to sort of really control that. So we need to think about all of the other areas, how we're doing in all of these areas, and essentially apply green chemistry solutions to try to get some of these under control so that we can continue to exist on the Earth. So population, higher consumption. So not only is the population growth, but the consumption per person is going up. The global supply chains equals larger chemical footprints. So this globalization idea of, you know, trying to globalize everyone's economies, by definition, means that we're transporting chemicals further and further from where their original source is. That's huge transportation costs, not just the costs, but the environmental costs of transporting chemicals. So we have to process and extract more material. We have to discard them. Essentially, small inefficiencies in any of these processes gets extrapolated because it has large multipliers when it's extrapolated globally. And so therefore, when we talk about green chemistry and green solutions, we have to really look at the full system. So we can't be satisfied with looking at, you know, the organic chemistry that's done in my lab and say that I've developed a green chemistry process. It has to be looked across the supply chain, and that means that it takes a broad range of scientists, right? We don't need just chemists, we need engineers, we need biologists, we need all types of scientists to solve this problem across the supply chain. So doing the right thing in the wrong way is not enough. So again, a solution must be evaluated across its life cycle. And so, you know, biofuels, these are just some examples of, I think, that areas where we think that we've improved, and I think that we certainly have, but there's not completely, they're not solving the problem completely because, for example, biofuels, which is a huge contributor to reducing our reliance on petroleum. So that's, we think, if you just think about it from simplistic, replace petroleum with biofuels. And you're like, well, that's going in the right direction, right? We all can agree with that. But biofuels are competing with food, water, fertilizer, and land use, because that's essentially where biofuels are coming from industries that provide food, water, fertilizers for us. And so there's not a zero cost to using biofuels. There is a land use cost. And so we have to weigh that. Is that an effective way for us to be using our lands to replace biofuels, to replace petroleum, right? And it's not a yes or no question, but you have to look at the entire life cycle to be able to say whether that's a yes or no question. Because if we do replace all of our land that was making our food for biofuels, well, then we have to solve another problem, is where we're going to get our food from. Right? And so those are the unintended consequences. Water purification, again, so we can contaminate our water with all kinds of different things, and we can say, well, it doesn't matter, we can just purify the water. Again, there's unintended consequences because we have to use chlorine or other harsh chemicals to purify the water, right? So there's not zero cost to being able to recover the water. Renewable energy, so solar panels, wind farms, they all rely on scarce, precious, and toxic materials, right? And so those, again, have a lifespan. They are not going to exist indefinitely. So is it worth it to make a solar panel that it can accumulate, X watts of energy per year for 20 years? But what's the cost of the material that makes those solar panels, and is that worth it, right? And that's where increasing the efficiency of those solar panels can be extremely important. And that can apply to solar farms or any other new energy source. So again, renewable does not automatically mean sustainable. So again, this is an important distinction to be made, right? Is that what we really are looking for is not renewable energy, but we're looking for sustainable energy, because what we want is a solution to our problem that can exist indefinitely, right? If it's a renewable source like corn, so corn is certainly renewable, but because it's being used for so many other sources, that it's not sustainable for an energy source. The life cycle analysis determines whether the overall benefit is real. So what is displaced and what new burdens are created? So again, this is looking at problems sort of from a bigger perspective, as opposed to always focusing on a simplistic solution to the problem. So the water, clean water obviously is a public health necessity. So there's in every region, there's going to be ways that we have to purify the water if the city is going to deliver water to its citizens. And so essentially chlorine has been the most important disinfectant for water systems and for disease prevention. But that chlorine comes at a huge cost in terms of its cost, in terms of transportation, safety of chlorine, and the byproducts that can be caused by it. Solar panels, we talked about this. So again, this brings us to near the end, which is talking about why. So this was all a prelude to why green chemistry is important. And so essentially there's an important landmark book that was written now about 30 years ago that imparted these 12 principles of green chemistry, which chemists are expected to incorporate into any process that they're designing, whether it be research, technology, transfer, and or industrial use. So the green chemistry essentially translates its values into these core features. So I think it's important to go over these individually. So preventing waste is much more important than treating it after formation. And so this is, in Canada, we have like the 3 R's of recycling. So it's recycle, reduce, and reuse. And sorry, it's reduce, reuse, and recycle. And it's sort of a little bit of a mind-blowing experience is that I never realized why they put them in that order, right? It's reduce, reuse, recycle, right? And so if you think about it in terms of green chemistry, the first thing that we should be thinking about is reducing our use of any material, right? If we reduce things, we can make things more sustainable. Then the next thing we should do is reuse, right? So then if we can reuse things over and over again, that can lead to a sustainable society. The last thing is recycle, right? The recycle is the last solution to our problems. And that's where it's preventing waste rather than treating it after the formation, right? So it's reducing, reusing, and then recycling. Design safer chemicals and safer syntheses. So that's again thinking about the function of the molecules that we're using. Use safer solvents. Bring the feedstocks from renewable feedstocks. Use catalysts and energy efficient processes. Design for degradation. So this is really important in terms of life cycle analysis. So the life cycle of a chemical should be taken into consideration. Is that chemical, are we able to destroy that chemical in a fashion, in a time frame that's a human-based time frame, not thousands of years time frame. Monitoring and accident prevention. And these are essentially the ways that we should be thinking about designing new processes and or chemicals. So the way that I've traditionally looked at chemistry is the molecule, right? So the molecule is the structure, and the structure is the molecule. But we should not only look at that from a structural point of view, but think about it is that it's a future exposure. So the molecule is exposed. It's a process, how to make the molecule. It's a supply chain. So how do we generate the starting materials for that molecule? It's an end product, and then it's ultimately going to be a waste stream. So any chemical that you make is going to be all of these combined with one another. And so essentially the green chemistry expands the definition of this excellent chemistry. So we have to think about performance, selectivity, yield, safety, scalability, life cycle, and these must be considered all together. So again, we're asking chemists a lot now, right? Because we're asking chemists to get outside of their small niche area of research and think about these bigger questions, right? I think that's very challenging, but it's very sort of also, there's a lot of opportunities there to contribute to solving a lot of the problems that are currently ongoing and will continue to require chemists' input. So essentially, function without safety is not success. So this is just a few examples that, you know, if we had chefs that were saying that they were preparing delicious food, every once in a while you would kill someone, right? You would not accept that because you would be like, oh, but their cooking is so delicious, the times that they don't kill someone, right? That's not acceptable. And that's essentially what a lot of chemists historically have been doing, right? Is that we design a new material, it kills some people some of the time, but it's a fantastic material. The times that it's not killing people, right? That's not good enough. And so these are just some other sort of analogies that you can make as that other areas have a higher degree of safety because the externality is more obvious to the general population, and we won't allow chefs to kill people 1 in 10 people because they make it, but allow it because they make excellent food for the 9 people that they don't kill. And so as chemists, we have to be held to those same types of standards that these other industries or professions are held to as well. So here's sort of a sort of more closely related to what we do in our lab, which is synthetic chemistry. So we're designing new ways to make molecules. And so what we have to think about is not only that the yield is high, so the fact that we take molecule A and molecule B and we make product C and we make that in 95% yield, right? That's the historical way that my synthetic organic chemistry discipline has thought about things. It's that I want to make everything in 95% yield. But that is such a simplistic way of looking at the overall process. And I'm going to show you the other ways in which we can evaluate chemical reactions that is well beyond just the yield. So having a high yield is one aspect, but there's many other aspects that we need to take into consideration. So reducing toxicity, waste, exposure, energy use, and accident potential. And that's where green chemistry takes these criteria and puts it into the design of the process, not as an afterthought. So like not back rationalizing the process, but thinking about it as we move forward. So again, I think that sometimes when you hear these types of talks in terms of why green chemistry is important, it can become a little depressing in the sense that we have to show all of these examples of negative consequences of chemists. But I think that really it's giving us sort of this
out of the light that can come great beauty. And so essentially we're not looking at these failures as the end of the study, but the start of doing things in a much more positive and positively impactful way for all of humanity. And that's what essentially what we're turning to is the problem solving and the critical thinking skills, which are, scientists are trained to do. And I think we're outstanding thinkers. And I think that we need outstanding thinkers to solve very difficult problems. And that's where I think that if we can sort of align ourselves in the same direction, that there's going to be no problems that we will not be able to solve. And so this is, again, trying to end on a more optimistic note. So using chemical creativity to solve these difficult problems. We want to be optimistic about being able to solve these problems. We want to act responsibly, to understand that we do have a responsibility societally to creating better chemicals, and with conviction, which is to treat sustainability as part of this scientific quality, and to sort of promote that going forward in all of our research areas as we move along things. I think that will be a good place to take a break. We can start again maybe in about 10 minutes. I'll take it out. It's okay. How many people are on? All the time? How many people are on? And these are other graduate students? These are other graduate students?
The life.
Yeah.
Some people are external, and some people are some people of other institutions.
All in years?
I don't know. I will know tomorrow with the formulary of the president.
Grab a call. That copy would be good.
Pessoal, a gente vai fazer uma pausa de uns 10 minutos e a gente retorna daqui a pouco. João Paulo Rodrigues da Silva.
Okay, welcome everyone back. So we'll keep this second session a little bit shorter. So maybe we'll go for 30 to 40 minutes. Yeah. Any questions before I start? Anything you want to talk about? Clarifications? Can be about anything, doesn't have to be about the lectures. Okay, so green chemistry, we're trying, the concepts are trying to reimagine how we talk about chemistry. So again, these are a little bit outdated, probably green chemistry, the original, the sort of the groundbreaking book was maybe about 30 years ago now, but there's a lot of journals. This is the original book by Anastasis and Warner. And also there's a lot of journals that are dealing with this now, Chem Sus Chem, green chemistry, applied green chemistry. So a lot of different areas that researchers are contributing different progress in green chemistry. It's not just green chemistry, because we have to look at from end-of-pipe control to molecular design. So again, like I've said before, it's the whole process that we're talking about. And so we have to change this, the mindset, which is, the old mindset was we make something, we use it, then we treat it, and then we dispose of it. And that is essentially not taking into consideration the end life cycle and the disposing of our materials at the time where we're designing the material, right? So we're basically just designing materials for function and not thinking about that life cycle assessment. And so essentially what we want to do is design safer, make efficiently, use responsibly, and then be able to degrade or recover that material back to some core functional component that hopefully then can be incorporated into other materials going forward. And if you can design this way with the degrade component of it, then this becomes, that means your consumption goes way down for the particular materials. This is not take into consideration all of the factors, right? Because energy is an input for making a lot of these new materials, right? So how much energy is being used? And is that a recoverable process, right? Yes or no? Do you have to use petroleum-based energy, or can you use a renewable-based energy? And can it be a sustainable renewable energy, right? Again, that's the life cycle assessment, and we're going to talk about that going forward. Draw chemistry, looks like I think we'll skip that. So basically what we're looking at the end of this course is essentially what we want to be able to use is introduce more precise language that is used in the green chemistry space. Think about when we're doing research on a day-to-day basis that we're designing features that are incorporating green chemistry thinking and hazard exposure and life cycle. So the whole process of green chemistry. And I'll tell you just, my group, because we're interested in green chemistry, what a few things that we've incorporated into our structure is that, so I have a group of about eight graduate students and one postdoctoral fellow, 8 graduate students between master's and PhD students. And so we meet on a weekly basis as a group and we go through, problems in the literature, or somebody will give a research update, or somebody will come up with some propose a new idea, a new direction that we should be going in. And so this is the general way that I think most organic chemistry groups work in North America. This is the type of group meeting that we have. And so when we started to think more seriously 10 years ago or so about green chemistry, some of my students came to me more recently and said, we should talk about green chemistry at every group meeting. And that's what we've done now, right? Green chemistry is now a standing discussion item of every group meeting. And I think that's important because then it becomes not just something we talk about during this lecture, but becomes something which we more actively think about on a regular basis when we're doing the research in the lab. And sometimes what my students are coming to talk about in green chemistry is not some big research idea or something that could be published, but it's simply, is there a way that we can recycle our solvents and use them twice or 3 times when we're doing our research? Is there a way that we can recycle our glassware effectively, right? One of our students wanted to wash our glassware, but then we started to think about the life cycle assessment, and you want to wash your glassware. Like when I'm talking about glassware, I'm talking about disposable glassware. It's like, well, what's the cost of washing that glassware with acetone? Is that cost more than the cost of a new pipette or whatever you're disposing of, right? So it gets us thinking about, on a daily basis, life cycle assessments. It's a very small world. Like, we're not going to save the world by doing that, but I think it's a thinking and it's a process that we're implementing in our group that is powerful. And along those lines, we discuss safety at every group meeting, and we discuss concepts of equity, diversity, and inclusion at every group meeting, because those are the 3 pillars that I think are worth discussing consistently through our group. And again, not because we're going to solve those problems, but I think it's important to keep them in the front of our mind rather than in the back of our mind. And so that is the change in thinking that I'm talking about here. And so I'm going to start with what is green chemistry and what it is not. The 12 design rules for the principles of green chemistry. What are the drivers of why we need to move in this direction? Progress in different fields, including colors, materials, and industry sectors, and then future reducing hazards by design. So this is John Warner, who's the co-founder of Green Chemistry, and that's where I got these slides from Beyond Benign. He's involved in that as well. And this is essentially how they defined green chemistry in that original book, in theory and practice. And really, I think the key sentence is aims to reduce or eliminate the use and or generation of hazardous substances during the design phase of materials development. So again, we see this common feature repeating itself, the design phase, right? When we design things, we want to design them more environmentally friendly, more sustainable. And so essentially, the 12 principles of green chemistry are shown here. They include waste prevention. So what you want to do is that in a chemical process, how much waste are you generating? And waste can be in many, many forms. And again, I give you examples from a synthetic organic chemistry perspective, but you want to transform product A, starting material A, into product B. Well, it's one thing that you have to add in the reagents. So you have to add in a catalyst. You have to add in solvents to the process. You have to then purify your final material. How are you going to purify the material? You could do a silica gel chromatography. You can do a distillation. But all of those things are adding into waste, right? So if you do silica gel purification, you have to dispose of the silica gel at the end of the product. So the waste generated is everything in your process that's not your actual physical product. And green chemists have come up with measurements and ways in which we can measure how much waste is produced per product, and that is a valuable sort of measurement of how efficient your process is. Atom economy. So because we're molecular in our thinking about processes, so we know that molecule A transforms to molecule B, but molecule A is made up of a number of different atoms. So how many of those atoms in the molecule A are incorporated into molecule B, right? Sometimes you can do a reaction where 90% of those atoms are conserved in the product. Other times it's going to be 30% of the atoms. But what happens to the other atoms? The other atoms are essentially waste. So the more of the atoms in your starting material that can be incorporated into your product, the more efficient and green your process is. Less hazardous synthesis. So this often involves evaluating all the hazards of all of the reagents that you're using, not just your starting materials, but again, the solvent, the silica gel, everything else. Safer chemicals. So essentially, the synthesis should be less hazardous. They should involve safer chemicals, safer solvents, energy efficiency. So industrially, it's actually all reactions at room temperature are going to be the most efficient energetically. But you doing reactions cryogenically, so doing things below room temperature, is a hugely costly process industrially. Going up to higher temperatures is costly, but less costly than going to low temperatures. So this is something which, unless you talk to process chemists, it's not easy for us to understand in the lab, because in the lab, it's relatively easy for us to cool a reaction to 0 degrees Celsius, right? Minus 20 degrees is a little bit more difficult, but we can do it. We can go to minus 80 degrees if we use dry ice and acetone, right? So those things are relatively easy and not that costly in an academic lab, but in an industrial lab, that's a hugely problematic steps. So energy efficiency, and that's just one example of how we can use energy efficiency. Renewable feedstocks, so can we generate new molecules from different primary chemical sources? This is one thing that my research group is very involved in. So if we think about the history of the starting materials for the chemistry that we've developed over the are molecules that have come from petroleum-based starting materials. So whatever you order from, I don't know if you order from Aldrich or Fisher or whatever chemical company is providing you the chemical starting materials, those chemical starting materials, if you trace back their origin, are usually coming from some petroleum source. And so that means that everything that we're doing in the lab is petroleum-based. And that's because 150 years of chemistry, we took the first materials, the first products, which were things like benzene and toluene, which were byproducts of the petroleum industry, and we learned how to derivatize them. Because we were like, we have lots of this stuff, it's relatively cheap, so let's do chemistry on that stuff. And so we figured out how to do all this cool reactions on benzene and toluene. Now, what we have to do is take everything that we've learned and apply it to different starting materials. So bio-based starting materials are not going to be benzene and toluene. It's going to be things that are highly oxygenated, because the byproducts of the petroleum industry were low oxidation states, low number of oxygen atoms. And so the chemistry we developed was to increase the oxidation states of these molecules to make them into interesting functional materials. Now what we're taking is biomass-based starting materials, which are things like sugars and lignins. Now these things have oxygen atoms. And so now what we actually have to do is we have to remove oxygen to get them to lower oxidation states. And that is completely different chemistry. So the chemistry of the last 150 years is useful in some ways, but we need to reinvent a lot of chemistries on very basic renewable-based feedstocks, reduce derivatives. So when we do a synthesis, we want to make it as efficiently as possible so that we don't have to derivatize it into something which is, maybe a protecting group, something which is in the path towards the functional material. Catalysis, this is another area where my research group is intimately involved in, is that if you can develop catalytic methods where you can lower the energy of transition states, that can significantly lower the energy costs of processes. So catalysis and energy efficiency are intimately related. Degradation, so again, this is the life cycle process. So if you're going to develop a polymer, can you develop a polymeric material that at the end of its life cycle can be depolymerized back to its monomeric units and then repolymerized into a new functional material? Real-time analysis, so this is where analytical chemistry can become very important, right? So a real-time analysis means that if you're doing a chemical reaction at 100 degrees Celsius, if you can figure out the real time in which that chemical process is finished, then you don't have to heat that reaction for any longer than is required to get the yield that is needed. So that means that instead of heating a reaction for 12 hours overnight, which is a typical thing that an organic chemist will do, because you can come in, set up a reaction at 4 o'clock, and then you just leave it till the next morning and you work it up the next morning. But that reaction could have been done at midnight or 1 a.m. or 2 a.m. and you're heating it continuously for another 5, 6, 7 hours. That's wasted energy. So having really valuable analytical tools is really an integral part of being able to do green chemistry. And then accident prevention, so being able to store chemicals. So the example of having large amounts of methyl isocyanate on site when it's unnecessary and only needed part of the time is something which we need to take into consideration for these processes. So what are they, the 12 principles on the previous slides? They're basically all of incorporated into the core principles of toxicity, products, energy, That's in the United States, at least, that they were banned. But today, essentially, the reproductive systems are still being developed. So even though this is 50-ish years later, the reproductive systems in the United States, so therefore, designing life cycle and understanding how life cycles is very
So better.
besides reducing other related energy emissions. Nuclear could be involved, and of course, even though nuclear has its own unintended consequences. Increasing bioenergy production, increasing solar and wind power, increasing CO2 capture and storage, and improving energy efficiency, and essentially these are the main chemistry
areas where people are working in. So increasing efficiency, renewables, CO2 capture and storage, low carbon-based material, bio-based starting materials, and circular products design. All of these involve molecules, materials, processing, energy that is required in chemistry's expertise. Depleting resources may be strategic. So non-renewable resources are being used faster than waste. This is thing for science audience with self-evidence that petroleum takes millions of years to produce, and we're using up those resources hundreds. There's no way that we can make more trade based resources fast enough. And so we have to use these renewable feedstocks to go here, and this is where I reducing the derivatives and separations, designing for reuse, recycling, coordination. Again, I like to go through all of this is that to show that based on the developing more sustainable processes, the terminology, the language that we're using, based on the chemistry principles, right? So we see this again and again, design for and so this is where at the beginning where I said that part of the importance of the lecture is highlighting all of the chemistry principles. And part of it is also introducing the language so that we can be more precise in the language that we use in communicating about the industry and how we want to move forward. The green chemistry solutions improve safety and performance at the same time. So we don't want to do one of the if we increase safety, but we can't improve performance simultaneously. It would be very hard for us to convince end users to uptake that particular technology. So that's why we need to think about both simultaneously. We have to consider safety in the design, which we didn't do previously. But we also need to design better materials. If we design worse materials that are safer, that's going to be very hard to do. So essentially, a safer design would remove entire categories of downstream costs. And so essentially, a lot of times, depending on the chemicals, so does anyone know, how do we dispose this? Does anyone use dichloromethane as a solvent in their lab? Does anyone use any halogenated solvents? Halogenated strength fluids? So halogenated solvents, if you do use them, typically, again, I don't know what the regulations are in Brazil, but in North America, you have to have one container for halogenated solvents and one container for non-halogenated solvents. And why do they do that? It's because that non-halogenated solvents, they take it to a furnace and they burn it into smithereens so that it decomposes all chemicals back to basically carbon. So that's high energy intensive, but at least you get rid of all of the chemicals and you reduce it back to simple starting material. The chlorinated solvents, they bury it in the ground, right? So that's a terrible in terms of the sustainability life cycle assessment way for us to deal with that solvent. Right? So we're basically just saying we don't know what to do with this. We're burying it in the ground. We hope somebody else will solve this problem a long time ago. Right? So that's an example of storage and transportation. Is that it's not only storage and transportation of starting materials, it's storage and transportation of the waste that you create from your processes. The regulatory and disposal of it, so depending on the country, there's regulations for disposing of it. Again, if they're asking you to bury it in the ground, that's going to be a huge cost to do as a company. And because you're going to have to maintain that, you're going to have to probably test that site for a huge number of years until you're able to do it. Worker safety is hugely important. Obviously, you do want to compromise that. Reputation and training of the company
So these are all the downstream costs of having hazardous products. The thing about, and this is one of those things about where economics and the environment don't necessarily have to be at odds, because if we can take into consideration the life cycle costs of processes, the economics becomes much more interesting. So these don't have to be mutually exclusive. Most historically, companies have thought if we have to be environmental, that's just going to add to costs. But if you really look at the life cycle of processes, it's actually not adding to your costs. It's reducing your cost overall while still being environmentally friendly. And so I think that's why life cycle assessment is so important, as opposed to the cost of producing that single raw material in the absence of its external externalities that are paid for by society and not paid for by the corporations. Few more slides. Past and present, end-of-life solutions. These essentially waste treatment, waste control, waste disposal. These are necessary in what is done correctly in many industries, but essentially they act after the waste has already exists. And so this is essentially a backwards way of looking at things, is that we created this and now how are we going to deal with these issues? So essentially, again, they use treat, dispose, and so hazard is made after exists. So I showed you this before. This new chemistry model is that what we want to do is design safe, make efficient, use responsibly, and then recover value. Is there a way that we can recover the solvent that we use, the silica gel? Maybe we can't use it for the same purpose in the next cycle, but maybe there's another reason, another way in which we can recover and start to use. And so we essentially are recovering value from the products that we build. Again, prevention, so remember I said PR, reduce, remove, recycle. So reduce, preventing is usually more powerful than control, which could be on the recycling end, all of that stuff. So this is a circular mindset, so taking into consideration that whole cycle, whether waste streams can become feedstocks. So essentially something that's a waste stream from one product, one process, can be the starting material from another process. I think that's taking into consideration the whole system. Recover atoms and energy. So again, the atom economy, where I said before, like we take 100% of the atoms and incorporate them into the final product. That's ideal. If you incorporate only 30%, can you do something with the other 70%? Right? And that takes a lot of creativity to think about what is valuable about that other 70%. Design of materials for recycling and preservation. Polymer chemistry is an exceptional job in this area. Is designing polymers that can be polymerized and depolarized more easily. I think that's really ways in terms of recyclability and degradation. Use renewable and waste derived feedstocks to reduce dependence on non-renewable resources. Okay, I think let's stop here and pick up as well. I don't speak English very well, no, it's fine. I had to take part of the data. I really like when you say the same programs begin with the design. This is an interesting way to think, but I want to question. You and your group in Canada, do you think about how connect these ideas with the society, like education or connect with the schools? This is my question. Quem puder explicar melhor é o seguinte, a gente pensa essas questões sendo químicos, né, fazendo pesquisas, pensando produtos ou pensando processos, mas toda essa cadeia que a gente tem no mercado, ela conecta a gente que é pesquisador e também as pessoas que fazem as coisas acontecerem na sociedade. Então, minha preocupação
há uma conexão deles lá que fazem essas pesquisas com uma forma de integrar a sociedade a essas ideias, para a coisa girar de uma forma geral.
Saying something about if your research group has a extension project to talk about all of this green chemistry directly to the society or in schools, something like this.
That's a great question. So we do go to some high schools, so grades 9, 10, 11, and so we talk about these concepts to those students. But to be honest, we don't do that enough. Like it's one of those things where it's everything takes a lot of time. Your research takes a lot of time. My grant takes a lot of time. And do that. It's very difficult. But it doesn't mean that it's not important, right? Just like I said, students came to me and said, we should talk about green chemistry every week. And like, it's so obvious when I heard it, but I never thought of it. You know what I'm saying? So then I'm like, well, we're going to be green chemists. That's what we should do. But what you're saying is so obvious, but we didn't do it. But we should do it. And it's like, that's very important. And I'll tell you something that, and I don't get it in money. This is just pure because I believe the Beyond Benign website. Go to that, and they have like lecture notes that you can give to high school students. They have lectures that you can undergraduate students. They have lecture notes that you can give to elementary students. And who want to go, and they have actually experiments that you can show to the students. So with the Beyond Benign website, their mission is exactly what you're saying. It's to promote it to all levels of education. And they provide resources for you. They just need people to go out and do the publicity. But I think it's cheap. I mean, all the resources are in English, but I mean, with AI now, I think that it's pretty easy to convert it into easy.
Alguém tem mais alguma pergunta que gostaria de fazer? In your research group, what part of the process you most focus on researches?
Yeah, so also a good question. It's just like, I think that at the end of the day, it's like we are doing synthetic organic chemistry on a very small scale to develop reactions that might be more efficient. So the way we look at it is that we're trying to develop more tools that can be used for green chemistry applications. However, when I talk about life cycle assessments, I mean, we are not thinking about life cycle assessment because we're not producing an industrial product. And that doesn't mean we shouldn't be, but it's just like it's hard to say that we have a life cycle assessment for something which is a basic research question that we're trying to answer. So, I think all of these concepts are very important for us to keep in mind, but I also think that we can't all be doing it until we go into industry, right? And then when we go into industry, I think that all of this has to be incorporated. But when you're as a PhD student or a graduate student, I think the most important is sort of understanding those concepts and seeing if you can contribute positively to a portion, because you're not doing them. You're not producing a consumer product or something which is going to actually have that much of an effect economically or environmentally. I think that what you're doing is on very small maps, not in industries. But it's to say that all of the things that you do, that you are doing, could have an effect environmentally, because somebody could take your process, whatever you do, and commercialize it. And then the better, and this is where design is better than post deconstruction, is that the better you design your tool, the better they're able to implement it into something which is environmentally sustainable. Right? And so they're starting from a protocol. Whereas historically, we just want to make that product 95% yield, we don't care about anything. Then somebody might take mine, and then we would have to redesign it to be environmentally sustainable, and that would take them so much more work and effort and resources that they might say, forget it, we don't really want to do it. So what you're trying to do is, whenever you do, trying to pass it to the next person, 10 steps closer to being environmentally sustainable so that they can make it 10 steps closer, and then we all work because I think that's the way I serve strategic.
Thank you. Alguém tem mais alguma pergunta que esteja mais relacionada à linha de pesquisa de vocês, né? O pessoal da inorgânica, que mexe com catálise, o pessoal da síntese orgânica, síntese verde, né? O Sérgio mexe muito com a parte de síntese verde, se eu estou correta, de green synthesis. Se vocês quiserem falar alguma coisa sobre a pesquisa de vocês, alguma parte que vocês acham que tem alguma conexão, pode ficar à vontade. Ok.
The synthesis of new drugs. And green chemistry is a very wide and interdisciplinary topic. So when you synthesize a molecule for the first time and you evaluate the biological efficiency, you still need to worry about the environmental impacts of the molecule. And I think that a complete study takes a lot of time and people. And what is the bare minimum we have to worry when it comes to when we talk about green chemistry, to make a publication that not covers all of the 12 principles, but make the discovery a little bit more friendly to that topic?
That's a great question. I think that we're going to go over some of these concepts over the next few lectures. But I would say things like ecology, impact, and materials. There's like these three essentially
three quantification tools, right? So one of them is what I said before, is measures how much atoms of the starting material are in the product. The other one measures how much product is being formed divided by the total number of waste. Those two numbers can go a large way towards saying whether you have a green process or not, right? Because one is like the number of, because the yield, on top of the yield, right? So you get the yield, you get the atom economy of your transformation, and you get the how much you make over how much you create by how much waste you create. And those three things can really give you a good idea of how, and it might not give you a great idea of how green your process is, but it's something to compare against other people. You know what I'm saying? Because then it's like, okay, you have 95% yield, your atom economy is 30%, and you create 1 gram of product over 100 grams of waste. Well, then compare it to somebody else, and they create 1 gram of product over 10 grams of waste. I mean, then their process is better for waste, but then you have to compare atom economy. So it's like they might be better there, but maybe your atom economy is better. And then it's a nuanced balance between all of those things, and all of that doesn't incorporate energy consumption, because then it's like, okay, my reaction was at room temperature, your reaction was at 100 degrees Celsius. So it's just that. So you're asking a good question. I think those numbers are something that a green chemistry journal would ask for, but to really evaluate the whole process, you really do have to evaluate all of the principles as it applies to your reaction. To really say which one is better or not. But But what you're asking about is essentially what we do. We don't do it all. We look at a few things and we compare so that we can put it into context. Okay, thank you so much. And like I said, if anyone has anything they want to talk to me about, please feel free to ask anytime.